Okay, good evening, everyone. I just heard a couple of good evenings. See, this is my style, right? I mean, I need a couple of them again. Good evening, everyone. Good evening. That's much better. So, yeah, I hope you had a good day today, and are looking forward to day 2 tomorrow. But before that, we want to end this day with a bang, and we have some sort of I'm calling it an evening keynote, right? And we have a very interesting, educated personality to do that. And it's my pleasure to introduce Ajay Kulkarni. Ajay is the CEO of a startup called as Timescale DB. To give you a brief profile about Ajay, his previous startup was acquired in 2011 by GroupMe/Skype/Microsoft. And he has done stints at Microsoft, Citigroup, and several startups before that. He holds a bachelor's and master's degree from MIT in computer science. And when I say MIT, I don't mean the one in Pune, right? So it's the MIT that we're talking about. And add to that, he also holds an MBA from MIT Sloan School of Management. So it's a privilege to introduce him, and he'll be giving his keynote today. Before we start, just a few more announcements. So as I mentioned in the morning, we are going to have a dinner tonight, a social event which starts at 7 p.m. The dinner will be held here, and a few dinner passes are still available, so if anybody wants to purchase them, they could do so by going to the reception. If there are people from Big Binary sitting here, is there anybody from Big Binary here? No? Anybody from Society General? So I have a gift voucher for somebody from your group, so I'll hand that over to you. So. Importantly, in the dinner, we will be serving one complimentary drink. So a soft drink or a juice or a beer is on the house. If you want further drinks, that is on your house. So you have to so you have to pay. You can buy it by paying cash. I look forward to having all of you at the dinner so that we can interact further. Without wasting much further time, let me hand it over to Ajay.
Okay, hello, hi, how are you? My name is Ajay. I'm the co-founder CEO of Timescale. From Timescale, we also have my colleague Matt in the front row, and we also have my parents who are also here in the front row. So the hard questions you can send to Matt, and the even harder ones send to my parents. So I'm here to talk about, I think, what is a really interesting topic, which is using Postgres as the foundation for IoT applications. How many people here are familiar with IoT and the Internet of Things? Yes, yeah, it's very cool. I think we're here because we're very excited about Postgres. And typically we think about Postgres as a replacement for other relational databases. One thing that I'm going to talk about now, which is something we found is really interesting, is that Postgres has a lot of potential for quote-unquote NoSQL applications as well. But we'll talk about that. But before we start, a quick introduction on Timescale. We're an open source time series database that is packaged as a Postgres extension. We're based in New York. And some of you may have seen the news, but a month ago we announced that we've raised $16 million in financing from some of the top investors in the world, including Benchmark Capital, New Enterprise Associates, and Two Sigma Ventures. But let's get back to IoT. When people think about IoT, I think today it's become very trendy to talk about IoT. And as a result, sometimes the meaning gets lost. So I want to start off by talking about what IoT means to us. What we found is that the computing industry moves in waves. You think about initially it started off with vacuum tube computers to mainframes to desktops to smartphones, right? And with each wave, you end up with computers the size of this room to computers that are on your desk, the computers are in your pocket. The computers become smaller and smaller. They become more and more powerful, and they become more and more ubiquitous. And what we're finding now is that we're actually entering a new wave of computing where the technology isn't just in your phone, but it's in all your things. And I think that's what's really exciting about IoT. As a result of this wave, IoT data now is emerging in more and more places. We see it in industrials and in manufacturing. We also see it in the smart home. Some of you are probably familiar with the Amazon Alexa and the Google Home products. Of course, we see it within transportation and logistics, which is, I think, cut off the screen. But transportation and logistics, two really interesting companies right now are Uber and Ola. And their business, if you think about it, are time series data businesses where they have to track moving assets across time and space. There's also the agricultural industry, where a lot of our food now is being deployed in systems that have sensors to increase crop yield so we can feed everyone, which is, I think, a very noble cause. And of course, the utility and energy space, where we think about where we get all our power. As a result of this whole wave, what we found is that we're living in an era of the rise of machine data. Can you see, am I blocking the way? It's good? Okay. We see the rise of machine data where and the volumes are much greater than anything we've seen before. These are some industry analysts' estimates where we have 44 zettabytes of data by IoT devices and by 2020. And a zettabyte is a million petabytes, so it's a lot of data. And you might ask, how do we get that much data? Well, one data point is that connected cars. So one connected car generates 25 gigabytes of data an hour. An hour, one car, 25 gigabytes. Right? The scale of this data is unprecedented. And as a result of this rise of machines, we have the majority of companies worldwide. 71% of companies worldwide now have IoT data. But the majority of this data is going unused because they don't have the right tools to analyze it. And I think this is where Postgres can play a really interesting role. As a result of the rise of machine data, we live in a really interesting point in time. And most people don't realize this, but 2017 was the first year where the number of connected machines on the planet outnumbered the number of human beings. And I think what's really fascinating is that human population growth is limited by our ability to reproduce, while machine growth is limited to, and also we evolve over thousands and maybe thousands of years, right? Machines are getting better, faster, cheaper, more powerful every year, and they're just limited by ability to produce more and more of them. So what's happening is really quickly is that we're getting outnumbered and surrounded by these machines. And then the question is, how do we make these machines, how do we leverage these machines to make our lives more productive and happier and more efficient? And we think the start of that is to understand the machine data. So question one is, what is machine data? Let's start with an example. And here we have machine data coming from three sources. You have a building, a farm, and a factory. And as these sources generate data over time, each row is a set of measurements at that time interval. And you can quickly see that this data set becomes a time series data set. Another more concrete example is, let's say you have a few devices that are generating, just measuring CPU. Maybe it's in a data center over time, and with each measurement, you have the device ID and maybe the device type. This is a little simple example. Probably a more concrete IoT example would be something like this, where each reading has multiple measurements. You have temperature and humidity and CPU, as well as some metadata. You include the device ID, the device type, and location ID. So when you look at this, does anyone see something interesting about this data set? What's interesting to me is that you have one set of time series data and another set of metadata. This actually looks very relational in nature. Right now it's denormalized. We have the metadata on each reading, but it doesn't have to be denormalized. And then that kind of suggests that maybe Postgres is useful here. So one quick point I want to establish is when we talk about machine data and IoT data, what we're really talking about is time series data with some metadata that describes it. And so then the next question is, should we use Postgres for IoT? Well, there are a lot of reasons why we would want to, right? And I think I'm talking to a Postgres crowd, so you probably all know this, right? But of course, we benefit from the 20+ years of reliability of Postgres. It's easy to use. You get full SQL. You get the power of joins, where, let's say you have time series data and metadata, you can join them at query time. We have flexible data types. Obviously, JSON support launched a few years ago, and that's very powerful for IoT. With tools like extensions like PostGIS, you get geospatial support for those, kind of geospatial applications. And of course, you get the broad ecosystem. But then the flip side is, why not use Postgres for IoT? Why not use Postgres for time series workloads? Any guesses? Come on. Sorry? The speed? Anything else? Sorry? Huge data? Yep. Anyone else? You guys are, I think, this concurrent data. Scaling. I think what everyone's talking about is actually scaling. And that's exactly right, is Postgres does not naturally scale well. And this is actually a complaint of every relational database, which is why in the past decade we've seen the rise of NoSQL. And I think we all know this inherently, but I think it's worth kind of like looking at it scientifically and understanding why Postgres does not scale well. So we did this analysis. In this graph, we're plotting the insert performance of rows per second as the data set grows. And when your data set is relatively small by IoT standards, let's say you have 5 million rows, insert performance is fairly flat. But as soon as you start adding data and you get into the hundreds of millions of rows, you see two things that are very troubling. Number one is that insert performance becomes much more variable, right? Where 1 second you might have maybe 15,000 rows a second, but the next insert may have 100 rows per second, and the average performance decreases over time. Any guesses on why this is happening? Sorry? Oh, I can't hear you. Yep. The challenge is what you're seeing here is the difference between memory and disk. At this point, when you only have maybe tens of millions of rows, all your data can fit inside memory, right? But as your data set grows, as you're inserting data, you're increasingly swapping to and from disk, which is why if the data set you need to write is in memory, you're fine. But you have to swap the disk, then it falls off a cliff. And as a result now, not only is the IoT workload less performant, it's unpredictable, so you don't really know what to expect. And then I know I'm talking to a Postgres audience. I know some of you are thinking, maybe all of you are thinking, what about Postgres 10? Doesn't this solve this problem? It doesn't, but I'll explain why in a few minutes. So then, of course, the next question is there a better way? Is there a better way to scale Postgres for time series and IoT workloads? And we believe yes, and that is what we built. So Timescale DB, again, we're an open source time series database. We're scalable, and we support full SQL, packaged as a Postgres extension. And I mentioned open source, we're Apache 2 licensed. At a high level, Timescale is easy to use. In fact, we look just like Postgres to the outside world. We support the full Postgres ecosystem of commands and functions. So you can use anything in the Postgres ecosystem to talk to Timescale. It's highly scalable. So not just insert performance, but also storage-wise. We've had customers who've scaled a single node to hundreds of billions of rows while sustaining the same insert performance, and I'll explain why in a few minutes. And it's quite reliable. As you all know, Postgres, you have 20 plus years of development. We inherit all that reliability, and we inherit the entire ecosystem. So any Postgres, tooling, backup support, all works with Timescale out of the box. And this is the result, is that, as you might remember, the Postgres graph started like this. This is that same experiment, but taken out to 1 billion rows. And one thing you find is that at 1 billion rows, instant performance it's pretty bad. While with Timescale, there's some variability, but it's within a pretty high range. And where we're ending up with 20x higher inserts versus vanilla Postgres at scale. I think the next question should be, how? How do we do this? And in particular, you might ask is, how does a relatively new company, a database startup, how does it beat some of the best minds who've been working on this for over 2 decades? And the answer is that we're solving a different problem than Postgres solves. The answer is that time series data workloads are different than what you typically see than the typical OLTP workloads you see with vanilla Postgres. When you think about OLTP, you probably think of we think about the canonical bank example, Or maybe I send you 100 rupees. So in one atomic transaction, Postgres needs to debit my account and credit your account. So as a result, a lot of most of the workloads are primarily update oriented. The updates, the writes are randomly distributed. Your account ID and my account ID may be in completely different servers or partitions. We don't know ahead of time. And the transaction is touching multiple primary keys, so it's actually quite complex. Time series workloads are actually quite different, and it's a little bit simpler. As you might remember from the example we had earlier with the data from the building, the farm, and the factory, is that the workloads are primarily inserts. They're primarily written to the most recent time interval, and the writes are associated with a timestamp and a primary key, and the primary key is typically device ID, user ID, or customer ID. And so as a result, we actually end up solving a different problem than Postgres. So we can make different optimizations that lead to much higher performance than you would get otherwise for time series data. Let's look into how it works. So this is the example we had earlier. The first thing we do is we automatically partition your data by time. We say, you have some older data, and some more recent data, and we partition it, by time. And these time intervals can be manually specified, or it can be, automatically adjusted. It's up to you. And then we partition automatically by space. And space means any type of partition key you want, or any number of partition keys that you want. It could be, again, a device ID, a user ID, an account ID, a customer ID, right? And we employ hash partitioning to evenly distribute the data across the partitions. And as a result, you end up with these n-dimensional chunks. And each chunk represents, for a given time interval and for a given range across space, it represents all the data, all the time series data, for those intervals. Each of these chunks are represented as Postgres tables. And so what we essentially do is right-size each of these tables such that all of the data and all of the indexes fit inside working memory, such that you avoid the expensive kind of thrashing and spilling to disk. But most importantly, step one is all these partitions, all this stuff is actually happening automatically behind the scenes. But what the user sees is something we call the hypertable. What the hypertable is the abstraction of a single table across all time and space, such that even if all of your data is in maybe hundreds or thousands of chunks, all you see is a virtual table on top. And the way the virtual table works is, if you want to insert data, you insert it to the hypertable, and Timescale will automatically route the tuples to the appropriate chunk. If you want to query data, you query the hypertable, and we'll automatically, using constraint exclusion, identify which of the chunks have the data that you need, and we'll do distributed query optimizations to get that data. But even data management, if you're creating indexes or triggers or constraints, you create those on the hypertable, and we will automatically propagate those changes across all your chunks. Even if you are writing data, let's say you're writing data, so here we're routing tuples to the appropriate chunks. Once you need new chunks, we will create them automatically, so you don't even have to worry about it. And so as a result, it gives us performance benefits. This is the graph we saw earlier, where again, at scale, we're seeing 20x higher inserts from Timescale over vanilla Postgres. And this is, for this machine, which I think it's a pretty lightweight machine. It's an Azure VM. It's an 8-core machine with, I think, 16 gigabytes of RAM. So it's actually pretty lightweight. But we're already seeing, over 100,000 row inserts a second. And in this case, each row has a timestamp and 10 columns. But this is batching your inserts. If you do single row inserts, you see slightly lower performance as you'd expect, but it's still higher than Postgres, at scale. And so here, we're seeing, maybe 15,000, 14 and change rows per second at single row. The benefits aren't just on the insert side, but also see better performance improvements on the query side as well, where we see for simple queries like table scans and column rollups, we find that we're no slower. We find that we're no slower than Postgres. But where we really shine is for the more complex queries like group bys and time-ordered group bys, where you get up to 10,000 times faster queries. And even deletes, we get 2,000 times faster deletes. Deletes are actually really interesting. Any guesses why deletes are interesting? Sorry? You're a step ahead of me. That's incredible. Yeah. So deletes are interesting because with time series data, you typically phase out old data because maybe you collect data at a minutely basis, but overnight you aggregate it into daily or maybe hourly aggregates, and you delete the raw data. With timescale, when you're deleting data, you actually just drop the chunk, as opposed to having to delete individual rows and having to undergo expensive vacuuming operations, which is why we get 2,000 times faster deletes. You might say 10,000 times faster queries, like, that's kind of crazy. How do you do that? So let's look at an example. In this example, let's say you have a time series table called readings. It's collecting sensor readings. And let's say you create an index. Let's say you create an index on that table on time, as you would. And then you run a query where you say, hey, give me the average CPU by minute for the past 10 minutes from readings. And another question I have for you is, will Postgres use this index for this query? Sorry? It should, right? It won't. Why won't it? Right. Because a function is using the select statement, Postgres doesn't realize that date trunc preserves the same inherent ordering as time, so that it thinks that the output of this is totally different than the input, so it doesn't rely on the index. Conversely, timescale understands time. Timescale understands that if your raw data is, let's say, it's by second, and you're aggregating it by minute, those aggregates are essentially ordered in the same exact ordering as the raw data, such that you can still use the index on time. And so we force the query planner to use the index, which is how we can get 10,000 times faster queries. Here's another set of benchmarks. So with timescale, we plotted it out to 1 billion rows. One of our customers, who's a large enterprise computer company, has much more better resources than we do, and so they actually scaled timescale successfully out to 500 billion rows. You might remember that graph looked like this, right, for timescale insert performance, but we stopped it at 1 billion. We always assumed that it would continue at this level because that's how we're designed it, but we weren't able to test it. They scaled it out to 500 billion rows, and while maintaining 400,000 inserts a second, seeing 70% faster queries. And at this workload, they were actually creating chunks every 4 to 5 minutes, and they essentially had, at steady state, 50,000 chunks. So imagine it's not on one instance. So imagine one Postgres instance with 50,000 partitions. 50,000 partitions. In this example, you can't create these manually, which is why you need something like timescale to do automatic space-time partition. OK, so Postgres 10. So speaking of partitioning, what about Postgres 10? Why doesn't Postgres 10 work? What about declarative partitioning? We feel that Postgres 10 is a great step in the evolution of Postgres. We're very excited about the development. But one thing we found is that it's actually still a little lacking for time series workloads. And I have 2 reasons why. The first reason is ease of use. It actually requires a lot of manual work. So let's say you're setting up 2 side-by-side instances, Postgres 10 and timescale, and let's say you wanted to set up a table with essentially 4 partitions by device ID and by time. First thing you would do is you would create the kind of partitions by device ID, partitioning by range, and then you'd create kind of sub-partitions for each of the time intervals. And then you'd end up creating indexes on time for each of these partitions. Now you have 4 partitions, essentially by time and by device ID, and then you can start inserting data. With timescale, it's just two commands. First, what you do is you run a command called create hypertable, which converts an existing Postgres table into a timescale hypertable. As part of this command, you specify the partitioning key, so in this case, device ID, and you specify the number of partitions that started with 4. And then you start inserting data. But that's not just it. You start inserting data, but let's say you keep inserting data, and now your 4 partitions they're quote unquote full. With timescale, you don't have to worry about it because we will create the new partitions as necessary. But conversely, with Postgres 10, once these are full, you have to manually go back and create the new ones. So again, with timescale, you don't have to worry about partitioning. It all happens transparently behind the scenes. The second limitation we found with Postgres 10 is actually around insert performance. Again, Postgres is highly designed, is optimized for OLTP workloads, and we're designed for time series. One difference in those two workloads is the number of partitions you might have. With OLTP, maybe you might have maybe 10, 20, maybe 100 partitions tops. And as a result, your insert performance maybe drops a little bit, right? And you're fine. With time series data, you might end up with thousands, or in the case of that one customer, tens of thousands of partitions. Postgres 10, unfortunately, for each insert, ends up locking each of your partitions such that once you're out here, insert performance falls off a cliff and essentially becomes unusable for time series data. These are for single row inserts. For the sake of completeness, we also plotted it for batch inserts. And for batch inserts, you end up pushing back the problem a little bit, but you still see a significant drop off. And as a result, you can't use Postgres 10 for time series data. So it's worth pointing out, we talk about all these performance benefits of timescale, but one thing is worth stressing is by using timescale on top of Postgres, not only do you get these performance improvements, but you still get all of the benefits of Postgres. All the benefits we talked about earlier. You get reliability, ease of use, joins, JSON, geospatial, the ecosystem. And I want to dig deeper in a few of these using IoT examples to kind of provide more concrete context to why this is useful. So number one, joins. So before timescale, maybe you stored your time series data in a NoSQL database and your relational data in a RDBMS. So as a result, you end up with an application that needs to talk to two different databases. And anytime you need to do joins across those two databases, you end up building a lot of complex join logic in the application. Conversely, with timescale, you can simplify your stack. You can have your relational data live alongside your time series data in the same database, such that when you're querying across those two data sets, you're joining them at the query level using joins. And again, this leads to operational simplicity because you're only managing one database, but also application complexity because you don't have to build this complex logic to join. This is actually not as useful in the cloud, but we found in IoT is actually very useful at the edge. Because on the edge, we have some customers who deploy timescale on, say, gateways on site. And on gateways, it's hard enough to manage one database, let alone two, which is why they essentially gravitate toward timescale to have a simpler operational stack on the edge. Another benefit is a geospatial temporal analysis. We talked about this a few times, but here's a concrete example. In this example, we're actually looking at, we're counting the number of trucks leaving the Los Angeles region by day, and we're summing the total weight, for the last 30 days. And what you essentially get with timescale is not just the benefit of time series analysis, but paired with PostGIS, you get geospatial temporal analysis. This query actually highlights, this is in a box because this is actually a new function that we added to timescale, which kind of leads to my next point, which is our benefit isn't just scale. One thing we found with Postgres is that because it's not designed for time series analysis, it's actually lacking even in ease of use with kind of functionality. So what we've done is we've added a set of functions to make time series analysis easier. One of those is something called time bucket. Time bucket essentially improves on date trunk. As we all know, date trunk allows us to aggregate by a minute, an hour, a day. But with IoT, you often need more granular time aggregation. You might need to aggregate by 5 minutes, 6 hours, 5 days. So then we added is this time bucket function, which essentially allows us to do that. We also added support for what we call our bookend functions, last and first. These are important because in IoT, let's say you're aggregating by 1 hour intervals. You're looking at the average you're looking at temperature 1 hour intervals. For that aggregate, you may not want the mean, the min, or the max, but you might want the last temperature reading, right? Or if you're looking at a moving vehicle, let's say a truck over time, and you're aggregating its position by hour, you may not want the average location within an hour. You might want the last location. These are actually quite hairy queries, very complex queries in vanilla SQL, which is why we, and by we I mean like really Matt, wrote these two functions to essentially make that type of analysis easier. There are a set of other functions, including histogram, and there's more that you can find in our docs, docs.timescale.com. And there are also some internal query optimizations that kind of work passively behind the scenes. For example, like the time-oriented group by where we said the 10,000 times faster improvement. These are more kind of benefits that you get by using timescale. So in short, we believe IoT isn't just a buzzword. It's not just this trendy thing. It's actually the future of computing. And I think the core of IoT isn't the thing, but it's actually the data the things collect. And there's a lot of talk today about new databases that you might need, or new platform, new systems for IoT data. We believe the answer isn't a new database, but a very old one. We think it's Postgres. And we think by using Postgres for IoT, you benefit from the reliability of the 20 plus years of Postgres work. You benefit from the ecosystem. You benefit from the community. But when you pair it with timescale, you essentially get the performance improvements. So you kind of unblock some of the scaling problems we had earlier. You get some time series analysis help. And using that as your foundation, then you can then build your IoT application. You can then rely on other tools within the IoT ecosystem that work with Postgres, including message buses like Kafka and RabbitMQ, data processing frameworks like Apache Spark, visualization tools like Grafana and Tableau. I mean, you know all these things, but Tableau is actually really interesting. Grafana is interesting because they just launched support a few months ago, which I think talks to the growth of the Postgres community, right? And of course, you get web frameworks, ORMs like Rails. And so, like, to bring this back to the title of the slide, I think a lot of people are trying to build new IoT applications. We think the answer to building an IoT application is actually Postgres. We think even though Postgres was not designed for IoT, it has become the inadvertent IoT platform. And if you're looking at building IoT applications, I would kindly suggest you look at Postgres with timescale. If you're curious to learn more about timescale, we're open source. We're on GitHub. It's Apache 2 license. We launched less than a year ago. In that short period of time, we've already been deployed in production around the world. We just passed 100,000 installs. We passed 4,000 stars just last week, so we're rapidly growing. If you want to try it out, it's actually quite easy to install. Create extension timescale.db. You can run this on your existing Postgres instance. If you want to migrate data, all you do is you create like a new table with the same schema as your old table. You convert it into a hypertable, and then you just insert data from the old table to the new table. So it's data migration is actually really easy. Because of our growth in the $16 million of financing, we're hiring. We're primarily hiring. We're hiring across the board in engineering and non-engineering. We're primarily hiring in our New York and Stockholm and Sweden offices. But if this sounds interesting to you, or you think this might be a good fit, we're happy to talk, even if you're not in those locations. Matt and I are here. We have a booth outside, and we welcome any types of questions. So in summary, timescale essentially allows Postgres to be used as the foundation for IoT. And if you have any more questions, I'd love to hear them now. Thank you. Mm-hmm. Please. Yeah. 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 Matt, do you want to help answer that? So the question is the way you tune Postgres. Do you have to tune timescale the same way, or?
So all of the regular knobs that you would have to turn on Postgres, you still have to turn, but at least for a lot of memory settings that exist in Postgres, we are a lot less sensitive to your settings because you don't hit that performance cliff as you would on regular Postgres. But I mean, one of the beauties of Postgres is that there's streaming replication. There's a lot of these other features that you can use. And if you do use them, you need to configure them the same way you would plain Postgres.
Thank you. Does that answer your question? Okay, cool. Yeah. That's right. I should also add that we have a pretty active support channel on Slack. So if anyone starts trying timescale and has kind of tuning questions or performance questions, or the queries aren't as fast as you'd expect, we see that typically with a few tuning changes, you can see vast improvements. We should invite you to join us on Slack, and we can kind of give you real-time support.
And for a lot of like your basic setup, like the default settings, they get you pretty far. So.
Other questions? Yes. Sure. Yeah. So today timescale is a single node only, and by single node only, I mean we still support streaming replication. You can't just scale out yet. What's interesting is scaling is kind of interesting, where on a single node we actually allow you to scale up easily by adding disks, and so the nature of time series means that because your inserts are their most recent intervals. A lot of our customers have been able to just, keep scaling up by just adding more and more disks. And that one customer that had, 50 terabytes of data, 500 billion rows, they had I think 24 1.2 terabyte drives. One thing we're working on for this year is the ability to scale out, but we haven't announced a timeline for that. But it is an active development. Yeah. Yeah. Not yet. What we found is two things. Number one is with Postgres, if you for example run Postgres and timescale on something like ZFS, you already get 4x compression, but for many people is good enough. What we've also found is most time series databases, because of their architecture, end up becoming very memory dependent, and so you get the cardinality problem that you often hear about. With timescale, because of architecture, we're actually very disked. We scale easily by adding disk, and disk is so much cheaper than memory that one thing we often ask is, why are you compressing? You're really compressing to save cost, And so compared to maybe system X allows you to compress, but if you're highly using memory, then sometimes the difference is negated. Yeah. Yeah. Go ahead. We work transparently and seamlessly with any of the Postgres connections with Spark. Yeah. Yeah. Yes. I'm sorry? Yes. Yeah, that's a great question. So the question is, have you benchmarked against any other time series database like Influx or Cassandra or something else? We haven't published those benchmarks yet, but at a high level, what we found is, and we actually have some data sheets at our booth that talk about this, against Cassandra. So I'll start with Cassandra. Cassandra is really interesting, where Cassandra scales out really well, but on a single node we're actually shocked. It's actually very underperformant. And so a single node of timescale, we're seeing 10x higher, 20x higher performance in Postgres, but 10x higher than Cassandra. And for a lot of these queries, because with Cassandra, you don't really get real secondary indexes. What people end up doing is, if you want to have the benefit of being able to query data different ways, you have to write the same data different ways. And so we essentially get faster queries, we essentially get faster inserts, and you get full SQL. Versus Influx, we see 50% higher inserts. On the query side, if you are doing essentially single column scans, Influx is faster. If you're doing anything more complex, we found that and we're going to publish this benchmark soon. We found timescale is faster. Number two, timescale supports more data types than Influx does. It supports. We found customers who've moved from Influx to timescale because it's more reliable, which is cheating a little bit because it's really the reliability of Postgres that they like, right? We fully embrace SQL, and while Influx is moving away from SQL, they're moving towards, they just launched their new query language called the Influx Functional Query Language, which is not like SQL at all. So one thing we found is that for some people who come from maybe a DevOps world where they're not used to SQL and their workloads are pretty straightforward, is maybe just looking at CPU over time, or even compression. Influx does have higher compression, but they do have the cardinality problem, so there's a trade-off. But we found for some use cases, Influx is the better option. But if you're actually building something where you need like a database, like something that is actually reliable, so full SQL, integrates easily with the rest of your stack, which you see often in IoT, then what you really need is Postgres and timescale. Yeah, does that help? Yeah. Sorry. Not yet. Not yet. Not yet. But one thing, well, two things. Number one is the open source version of Influx does not shard either, right? It's a closed one that supports clustering. And number two is what we found is, by scaling up by adding disks, people haven't eaten yet, but it is on our roadmap for this year. There's a question here around. Yeah. So right now, timescale is single node with read replicas. The reason why, and we've been working in clustering, but we've actually pushed it back. And the reason why is we found that a lot of our users who started off thinking that they needed distributed support ended up being happy with a single node with 3 or 4, maybe 2 to 3 read replicas. Like, look, if we have 10x higher performance than Cassandra, you can replace a 10-node Cassandra cluster with one timescale node with 2 read replicas. That said, we are talking, and we've had, customers who scaled to 50 terabytes, on a single machine, right? But that said, we are talking to people who are looking for maybe close to a petabyte of data, or they're looking for instant performance in the kind of millions per second. And for that, we'll need distributed support. That is on the roadmap for this year, and it's in active development. I should point out that our team actually is quite technical. My co-founder, who's not here, who I've known for 20 years, he doubles as a professor of computer science at Princeton, and a lot of our employees, including Matt, are some of his former students at Princeton University. And his background is actually in distributed systems. So, and it's actually not database, it's distributed systems. So when it comes to building out the distributed timescale version, we actually have some great ideas that we're in the process of implementing. Yes? Yep. That's right. Yep. Yes. Yeah. So 2 answers to that. 3 answers. First is that we are adding functions as necessary. You've seen some of them so far, like time bucket and first and last, and there's more in our docs and more in the pipeline. Some of these functions we're adding for specific verticals. One of our investors is 2 Sigma Ventures, which is one of the leading quantitative hedge funds in the world, but they're based in New York. And we're working with their time series team to build a set of kind of financial functions. So that's number 1. Number 2, we've also found that SQL is actually quite powerful. And we've actually been quite surprised by what you can do with SQL. So, often, until we have like a nice looking function, often we can still, solve someone's problem by providing them a SQL function that does the job. And the third thing we found is because we look just like Postgres, Stack Overflow is your friend, because often people have found workarounds to do some of these queries. But we're in the process of kind of improving this functionality. That's one reason why we think that our value isn't just scale. But if you look at our docs and you think there are certain functions that you need that we don't currently have, we're happy to hear them and we're happy to work on them. We take requests. What's that? Yeah. Mm-hmm. Yep. Yep. Yes. Yeah. Right. Yeah. No, I think that's where I think we can add and kind of make it easier. Where do you work? OpenTable, okay, that's why, yeah. But before you were in finance? Where? Bank of America. Okay. Okay, cool. Yeah, thanks. Yeah, just curious. Other questions? Yes, please. So this is where any migration tool that anyone else has written to migrate to Postgres. Yeah. Yes. Yeah. So any of the third-party tools that will migrate to Postgres will essentially migrate to timescale. You might have to do things a little different, like creating hypertables ahead of time. But we also work with customers to do that. What we found is, if we're building a brand new database, it would be a lot harder. But because we're packaged as a Postgres extension, a lot of the work's already been done by the community, and we just do the last mile, if you will. Do you want to talk about Prometheus really quickly? Are people familiar with Prometheus? So Prometheus is a really popular monitoring tool. We use Prometheus internally. What we wanted was a Postgres backend for Prometheus, and so we did two things. First, we built an open source extension called PG Prometheus that includes a special Prometheus data type that allows you to easily write Prometheus data into Postgres. We also wrote a kind of a timescale / Postgres Prometheus connector that's actually in the Prometheus documentation, and so they're promoting that. And then we also added timescale, because obviously if you're just starting Prometheus data, you need to scale faster, scale better than what you can do with Postgres initially. These are all in our GitHub. We in fact have a Docker image that includes all of these together. And also now with Grafana support, you can essentially have Grafana on top of timescale, which then is pulling in data from Prometheus. Any other questions? Well, thank you very much. We'll be here tomorrow as well. Tomorrow morning, Matt is giving a technical talk, a more technical talk on the database and how it works I think at 11 a.m. So if you'd like to learn more, especially more on the technical side, I encourage attending that. We also, for those of you that are local in Bangalore or maybe staying around, we're hosting a meetup on Saturday with Open Source Bangalore. The meetup's at 10 a.m. at Microsoft, and we already have, I think, 200 RSVPs, so it's like another conference. But we have essentially that meetup on Saturday. And then for any of you that are based in Pune, we are hosting two meetups, one on Sunday, one on Monday. The Sunday, these are all on meetup.com, or we can give you the information afterwards if you want. The one on Sunday is focused on DevOps. We'll be talking about the Prometheus connector. That's in the afternoon. And the one on Monday is in the evening, and that's more around Postgres and open source. So again, if you want to learn more, I encourage you to come, say hi, ask us at the booth, or check out the talk tomorrow morning, or either of the meetups in Bangalore or Pune. Thank you very much.